talked about on Friday local linearization, and basically what you're dealing with local linearization, we're looking at equations of tangent lines. Okay, when you linearize a curved object, you're looking at that small section that's still curved, but since it's still curved, it's not exactly linear. But if I take a small enough section, I can say it's pretty darn close to being linear. So you're looking at the idea of tangent lines when you talk about local linearization, which is sort of nice because that was a little bit easier thing as we go back and we look at the idea of linearization or a tangent line, how we determine our tangent line. Then we started looking at approximations of radicals, and we can use local linearization to approximate our radicals. We look at the square root of 103. We have, looking at a local linearization and simplifying a little bit, this idea of a slope. And when we break it out, we can talk about our derivative times a value here plus a value here. If you also think, another way of thinking about it, point slope form of an equation. Point slope form of an equation. We have slope x minus x1 is equal to y minus y1. We can add our y1 over. And what that turns into is it turns into this. Here's our slope here. Here's our two x values. Here's my y value here. So that's another way of thinking about this approximation. We take the square root of 79. Okay, square root of 79. X is your closest perfect square, cube, whatever you're talking about, to 79. Well, what's our closest perfect square cube to 79? 81. Our value that we're working with still is 79. This is what we're trying to find. This is our approximation. We're still dealing with the square root, so we're still dealing with a function f of x equals square root of x, which is x to the 1/2 power, and we have our derivative. This is a derivative that, as you go through derivatives, yes, we can use our exponent rule and bring it out, but hopefully you start remembering that if I have a square root of x and I take the derivative of square root of x, that's 1 over 2 square root of x. That's something, because we've done it enough, hopefully you can recall that. If not, you can always go back to the idea, this is 1 over 2, x to the negative 1/2 power. I can take x to the negative 1/2, this is going to drop it down the bottom, making the square root of x. So I have 1 over 2 square root of x. All right, so we have to find, let's see, our value of 79 is our function value at our perfect square. So we have f of square root of 81 plus f prime at 81. And then we have 79 minus 81. That's our two x values that we're dealing with here. Go ahead and simplify and find an approximation. So we have an approximation of 1 8 8/9, or 8.88888. And if I would take the square root of 79, do we get something close to that?
Yeah.
Now, once again, the closer you can get your guesstimate to that, the better off you are. Suppose you use the value of 64. It said x was 64. So what this turns into is square root of 64 plus 1 over 2 square root of 64. Then 64 minus, I'm sorry. Let's see, yeah. We have 79 minus 64. So this would give me 8. This would give me 1 over 2 times 8. And this would give me a value of 15. So we have 8 plus 15 over 18 over 16. So we have 8 and 15 sixteenths. 15 sixteenths is what is a decimal?
0.9375.
Which is a little bit different than what we have up here. This is a little bit further away than the actual square root of 74 or 79. Okay, so it's one of those things where the further you get away from your actual value, the not as close you have with respect to the approximation. When you look at the back with respect to differentials, when you look at the term differential, your differentials is your calculus notation for deltas. Differentials are calculus notations for deltas. So when you have a delta x, the calculus notation of that would be dx. Delta y, we have dy. So in the calculus world, f of x, which we know was delta y over delta x, which is our slope was our delta y over delta x, which is f prime of x turns into dy dx. If you multiply both sides by dx, what you're left with is delta y, dy is equal to f prime del dx. And once again, this is sort of nice to step back a little bit and not be too intense. We want to determine the differential dy dx. So I want to find dy dx. I want to find just the differential dy. So if I can take my delta y dy dx, I can take my derivative of this, which gives us what, Jacob?
3x squared plus 14x minus 9.
So to calculate our differential, we can multiply both sides by our dx. So dy is equal to 3x squared plus 14x minus 9 dx. This is going to be important as we advance onto into our last chapter. We're not quite there yet, but in our last chapter, we will utilize this to be able to take our dy dx and put the process into reverse and find what is our function. So if we take a look at y equals sine of, or e to the sine of x, I want to determine what dy is. So we first find dy dx, the derivative of y with respect to x. And then at that point, just multiply both sides by dx. Justin, what's our derivative?
E sine x times cosine x.
And then we can multiply by dx. So my differential dy is equal to, and I can leave it in that form, or if I want to put the cosine of x times e to the sine of x dx, that is fine. Or if you have it still left in this form, that is fine also. Either way is correct. Questions you have in regards to differentials? The idea of a differential, approximations, working through approximations. All right. Now on the worksheets I gave you, we're able to do everything. We're able to do everything? All right, well, what I was planning on doing is finishing up our notes and then allowing you to work on the worksheet for today. That was my goal. If you have everything done, then I'm going to leave tomorrow to tomorrow rather than try to push tomorrow into today. Check, once again, you can check your homework, see if you have anything that you have to do. You can finish out anything you did not complete, and we'll go with that. How's that sound? That work for you?
Yeah.
All right.
I go get my computer.